Okay, so this is a review of science and technology over the past 40 years, with a few smiles along the way, hopefully, and a few speculations about the future as well. The pace of scientific development is ever increasing. It's pretty much an exponential rate. So I thought I'd have a few couple of slides of speculation. But first of all, we'll start off with one or two jokes. So just to get you in the right mood, and then there'll be some funnies interspersed, hopefully between the serious stuff. So all information here is presented in strict accordance with the Encyclopedia Moronica. And the good news is my IQ test came back negative. Now, people have heard of the Heisenberg uncertainty principle, but I prefer the Heineken uncertainty principle because I'm never sure how many beers I had the night before. I'm reading a great book at the moment on anti-gravity, and I just can't put it down. The unofficial, unabashed scientific dictionary defines elementary particles as the dreams that stuff is made of. And there are 6 times 10 to the 23 guaccas in a guacamole, and this is also known as avocado's number. A tachyon is a gluon that isn't quite dry yet. And time is what keeps everything from happening at once. Einstein discovered that time and space are relative. I've discovered that the more time I spend with my relatives, the more space I seem to need. And I was going to tell you a joke about time travel, but you didn't get it. And I was thinking about telling a joke about chemistry, but every time I do, I don't get any reaction. And that's all the bad jokes out of the way. Okay, so, well, some serious stuff now. So 40 years ago, 1982, there was no internet. It came out of a thing called ARPANET, which was ways of connecting supercomputers. In particular, it was actually the American military, and then a thing called JANET evolved, which was the Joint Academic Network, and that was the beginning of starting to connect computers together in a resilient way as well. Of course, we all remember the early days of connections. It was via dial-up with modems and bulletin boards and things like Usenet groups, which are great, but obviously we've moved on a lot since then. And then we've got the World Wide Web, which came from Tim Berners-Lee at CERN. He effectively developed one of the first web browsers and the protocols that is behind web browsing. And then, of course, we've all benefited from broadband, which we're all using right now, of course. And then, of course, mobile phones emerged principally from things like car phones. But, of course, in 1982, they weighed kilograms. I had a friend who was actually a car dealer. He had a phone in a box, and it weighed about 2.5 kilos. And then in 1982 was the first artificial heart transplant using a thing called a Jarvik 7, which is an implanted pump. So 1982, the launch of the first communication satellite into orbit via the space shuttle. Donald C. Becker discovered the first millisecond pulsar. So pulsars are collapsed stars that emit radio frequency information at a very regular rate. Now this is an interesting one. 1983, Carey Mullis invented the polymerase chain reaction, which is a major discovery in molecular biology. And of course, that's been the basis of all these PCR tests that we've been so familiar with over the past 2 years. Absolutely key in genetic studies and genetic engineering. And then French doctors identified that HIV was actually the root cause, the virus which caused AIDS. 1984, they started to retrieve malfunctioning satellites using the space shuttle, and they could do repairs in space because of the size of the cargo bay. And then they discovered the ozone hole over Antarctica in 1984. In 1986, Voyager 2 photographed Uranus and discovered that it had moons. and discovered the 5 major ones, but now we know, of course, there are at least 27 moons of Uranus. The first high temperature superconductors were developed in 1986, and then the Soviet Union launched the Mir space station, and sadly in that same year the US Space Shuttle Challenger exploded on launch, killing all 7 astronauts on board. 1989, an asteroid came very, very close to colliding with Earth. This was a big one too. It passed Asclepius, past Earth at a distance of 425,000 miles. So it's just on the other side of the orbit of the moon, so pretty close. And geophysicists estimated that if it had collided with the Earth, it would have been an explosion equivalent to a 600 megaton atomic bomb. The problem was, they found out 9 days after it passed by. I'm happy to say these days, most objects of this type are known and regularly tracked. And then, of course, 1990, the launch of the Hubble Space Telescope, but it had, of course, a serious defect in the mirror. More of that later. And then in 1990 as well, the Human Genome Project started. This was a project to map all of the information in the human genetic bank, all of the stuff, if you like, that's in the 23 pairs of chromosomes in our genome. 1991, they discovered the massive crater buried in the Yucatan Peninsula, 66 million years old. And of course, this was the Chicxulub crater, as it's called now. It's 110 miles in diameter and varies between 3 and 5 miles deep. And there it is on the map, if you like. That's where Chicxulub is. And of course, that massive asteroid, somewhere between 6 and 9 miles in diameter, put paid to the dinosaurs. But what if the dinosaurs had developed their own space program? You know, they've developed a space program, flown off into space, and many years later, they're on the way back to Earth. And here they are, just about to return. Finally, we're home. Hope the monkeys didn't touch anything. But we've been monkeying around with rather a lot. So, 1991, carbon nanotubes discovered. One of the strongest materials ever discovered. And in 1992, Pope John Paul II acknowledged the Vatican's error in their past condemnation of Galileo, only 359 years late. 1992, the Big Bang became a household phrase. It was first theorized in the 1940s, but it wasn't confirmed until very much later. And there was a landmark paper in 1992, and it was essentially about the mapping of the afterglow of the Big Bang, which is called the cosmic microwave background radiation, by a NASA space telescope called COBE, or Cosmic Background Explorer. And this mapped all the minuscule changes in the microwave radiation that's left over from the Big Bang. And those tiny ripples are actually now where the stars and galaxies first began to form in the very early universe. And this work was awarded a Nobel Prize. And then 2 further cosmic microwave background space telescopes mapped the radiation. WMAP on the bottom right there, much more sensitive than COBE. And then Planck, which was even more sensitive than that. And they now map the cosmic microwave background radiation to enormous, enormous detail. So it's the oldest light in the universe that we can see or can measure. And it was released 380,000 years after the Big Bang, when the universe had a temperature of about 3,000 degrees. And this is what it actually looks like when you plot the map. And it's basically the cooled afterglow of the Big Bang. And the average temperature is 2.7 Kelvin. In other words, 2.7 degrees above absolute zero. And the fluctuations in this are only 1 part in 100,000. So it's quite uniform and quite even. And it's the best information that cosmologists have about the very early universe. And they're still studying this information in great detail, even though they stopped collecting it quite some time ago. But cosmology, we all know about cosmology. Lots and lots of theories in the in tray, very few proofs in the out tray. And then, of course, we back to the Hubble Space Telescope, which has taught us so much about the universe over the past 30 years. But of course, it had a wonky mirror. And this was a cartoon from about the time. And I thought this was particularly funny, very clever. So we've got a wonky mirror, and we've got distorted pictures of the moon. We've got distorted pictures of Jupiter. And then we've got wavy rings of Saturn. And then looking back at the Earth, we see the distorted and angry faces of the US taxpayers, because it only cost $2 billion to fix it. So they installed, using the space shuttle, of course, they took up CoStar, which was the corrective optics package, which fixed the mirror. But as I say, it took 3 years and $2 billion to fix that particular problem. So we look at the M100 spiral galaxy. We look at the first picture that was taken. You've got this fuzzy, horrible picture, which horrified the scientists at the time. And of course, the reason it went up with this wonky mirror was because NASA management, senior management, refused final testing of the mirror. Fortunately, they haven't made that mistake with the James Webb Space Telescope, which more on that later. So this is the after the fix. So you can see this beautiful image of a spiral galaxy M100, a much improved image. So, and over 30 years, of course, the Hubble has given us fantastic service. It's had to be repaired a few times, 5 different service missions, but it's told us more about the universe than any other telescope. But it could have thrown up some surprises, of course. You know, every time they put a new space telescope up, they get surprises. So it could have been quite embarrassing. I mean, you know, it could have proven that we live on a flat Earth. What would have happened if that had thrown up? 1993, Fermat's last theorem, which was first proposed in 1637, was finally proved. Fermat wrote in the margin of his notebook, well, I've got an answer to this particular problem, but I don't have room here to put it in. And only I wish he had, because it took nearly 400 years to just sort it. And basically, it's this formula here, a to the n plus b to the n equals c to the n for any integer greater than 2. And just trying to prove that took Andrew Wiles quite a few years, and some of the most advanced mathematics ever invented. Here he is, the chap himself. 1994, the Hubble Space Telescope confirmed the existence of a black hole in the M87 galaxy, 50 million light years away in the constellation of Virgo. And its mass was 6 billion times the mass of the Sun. So absolutely immense thing. In 1994, they observed, again using Hubble, the Schumacher-Levy 9 comet breaking up actually and landing and colliding on Jupiter. Some spectacular pictures. 1994 as well, the first of the breast cancer genes was discovered, BRCA1. There are now BRCA2 and others, of course, which has led to early diagnosis and treatment. 1995, the second US-Russian space docking occurred between Atlantis and the Mir space station. 1995, the first exoplanet or extrasolar planet was discovered, 51 Pegasi, 50 light years away from Earth. And of course, nowadays, we know a lot more. Then 1995, the discovery of the top quark. This was the last in the set of 6 quarks, was finally discovered in Fermilab in the USA. 1996, Pope John Paul II affirmed evolution by natural selection. Again, only 137 years late. And then Dolly the sheep in 1996 was cloned by the Roslin Institute in Scotland. And then in 1996, a new class of life completely. So a third branch of life, in addition to eukaryotic life and bacterial or prokaryotic life, was a new form called archaea, single-celled, simple, a bit like bacteria, but significantly different. 1997, there was a microscopic analysis of meteorite, which led to the belief in ancient Mars, life on ancient Mars. That was finally debunked. Pathfinder, the vehicle, the little rover, photographed Mars and studied it. So a little rover was called Sojourner, and the mission was called Pathfinder. But the very latest rover on Mars, of course, is Perseverance. And we've got one of the very latest pictures, breaking news. There we go. It's the latest picture from Perseverance. So until the 21st century, the scientists had assumed the universe expansion was slowing, and that gravity would pull matter back together again and slow the expansion of the universe. But in 1998, two teams of scientists studied things called Type 1a supernovas, which can be used as standard candles for measuring distances quite accurately in the universe. And they discovered, in fact, that the expansion of the universe was actually accelerating. And that led to the so-called dark energy hypothesis. But again, you know, it's amazing what we're constantly finding all the time. So now, along with antimatter and dark matter, we've recently discovered the existence of doesn't matter, which appears to have absolutely no effect on the universe whatsoever. 1998, human embryonic stem cells were isolated. And of course, these cells can be transformed into virtually any cells and tissues within the body, which promise new therapies. But obviously, the source of these cells was very, very controversial indeed. Obviously, people were very reluctant to use them, and also that led to bans on the research in America. 1999, Peter Gamble and his team at Bell Labs and Lucent Technologies came one step closer to creating the small, super thin cell phones that we see on the market today. They used a thing called micromachining to reduce the size of three crucial parts, electronic parts, and fitted them onto a single chip, which led from something like this brick, to the things that we have today. And then 2000, the tau neutrino was discovered. That's the last of the leptons, of six different leptons. It's all part of the standard model of particle physics. And this was discovered by again at Fermilab, by the donut experiment. 2001, a paper reported the initial sequencing work. They'd done 94% of the human genome and had published the first draft of the 3 billion base pairs that make up human DNA. 2001, the age of the universe was confirmed, again using Hubble Space Telescope, plus other things such as the boomerang balloon flights and other data, and set the age of the universe to be 13.7 billion years. And of course, now we know it's actually nearer to 13.8. 2002, solar neutrinos were seen to change via a process called neutrino oscillation, and they found that they must have a very tiny, but as yet undetermined mass. And they're still studying these in great detail. And again, a lot of that work is being done at Fermilab. 2002, this is quite complex charge parity violation. Basically, what it's saying is they've detected differences between antimatter particles and matter particles, because for all matter particles, there are equivalent antimatter particles. And what they found is an asymmetry in between matter and antimatter. And what this was telling them basically, or was beginning to get information which explained why, when the universe was created, equal amounts of antimatter and matter were formed and should have all annihilated. There should have been nothing left but a huge gamma ray pulse in the universe. But there isn't, of course. We are the material that's left over from that annihilation. So there must have been an asymmetry between matter and antimatter. 2002, anthrax toxin structure was determined, and that obviously led on to modern treatments for anthrax. 2003, again, this sad disaster, the Columbia Space Shuttle. This was damaged on launch, unknown to the NASA scientists, and sadly broke up on re-entry into the atmosphere, killing all the 7 astronauts on board. 2005, it was confirmed that higher levels of CO2 expected to be in the atmosphere by 2050 will actually cause trees to grow at a much faster rate. 23% is what they've actually measured. So if the atmosphere does become significantly increased in CO2, then we've got some hope that the trees will start to take that up in large amounts. But of course, we've got proof of climate change now. We know it's getting warmer. We can tell that, quite easily. Things must be getting warmer. And then, of course, we've got the effects of the Statue of Liberty in New York. She's shed her robes and is now stood there in a bikini. So we know it's getting warmer. 2005, the blueprints for the cell's protein factory were determined. This is the thing called a ribosome, which basically builds proteins. So what you've got here in this diagram, this thing is a ribosome. This is the DNA material going through the ribosome. Well, it's actually RNA, strictly speaking, but it's transferred from DNA. And then this thing here, all of the materials are coming in and are being assembled onto this, which is the structure of the protein which this ribosome is building. Now, these ribosomes are unbelievably complicated things, and they managed to determine the whole structure, which was incredible. 2006, some paleontologists at Chicago University, Neil Shubin and his team, showed the first evolutionary links between fish and the animals that evolved to live on land 275 million years ago. So this Tiktaalik rosea, which is an extinct fish-like creature with scales and the long body of an alligator, is thought to be the ancestor of creatures that began to live on land. But some discoveries are extremely hard to explain. I mean, how would you explain this? In 2007, skin cells, just plain old skin cells, were converted into stem cells. And this is a major breakthrough because using these techniques, they could create what are called pluripotent stem cells just from skin tissue, which means they didn't need to use embryonic stem cells in terms of research and also in terms of therapies that might emerge from the use of such stem cells. So now we've got many, many different sources of stem cells and have no need to use embryonic stem cells, which is a big relief. 2008, a new form of extinct archaic human was discovered called Denisovans. They're called hominins, which are the more modern branch of human type creatures. And evidence was found in a cave in south central Siberia, on the borders of Kazakhstan and China and Mongolia. And this is where it is on the map. You can see there's India, and this is where the actual evidence was found, where the cave is. And believe it or not, the cave, it was named after a chap called Denis, a Russian hermit who lived in the cave for many years. And they called the the new species denisovans in his honour. And what they actually found, they found more evidence since, but they found the finger bone of a female adolescent. And fortunately enough, there was enough material in it to analyze the mitochondrial DNA. If anybody wants to know what that is, I'll explain it later in the questions. So the first extinct animal was cloned. Of course, we all want woolly mammoths to be cloned, or a saber-toothed tiger to be cloned, or whatever, but that's still the stuff of science fiction. But the first extinct animal was cloned in 2009, and it was actually a Pyrenean ibex. Now, it was sadly the clone died shortly after birth, but it was still considered to be a major substantial advancement in science. 2010, chemists or physicists stroke chemists were looking for the so-called islands of stability. In other words, creating elements heavier than those that occur in nature, looking for, hopefully, a region where the elements created would be stable for a significant periods of time. And so they're building these super heavy elements in colliders, going way beyond uranium, and they came up with this tennessine. It's 117, bearing in mind that uranium is 92. So they've significant progress, but again, very quickly, they were trumped by this one, organesson, which is 118. But these things only live for a tiny, tiny fraction of a second. 2010, some colleagues, Gordon Anderson and his colleagues at CERN, created anti-hydrogen and managed to trap it. 38 anti-hydrogen atoms were created and trapped in the alpha experiment. So what they did was they took an anti-proton, which is an antimatter version of a proton, which is the nucleus of a hydrogen atom, and they added to that positrons, which are the positive version of electron or an anti-electron, and they created in this trap system 38 atoms of anti-hydrogen. And as we know, antimatter is, well, it's the most efficient fuel you could possibly get. It annihilates with proper matter with 100% efficiency, turning all the matter into pure energy. But it's very, very expensive to produce, extremely expensive. So we won't be using it anytime soon as a fuel in our warp drives. 2011, a paper described for the first time the atomic structure of a thing called a G protein coupled receptor. So what they did, again, this is very, very complicated protein structure. And again, they got the Nobel Prize for this. This is a major, major achievement in terms of working out these receptors, because they're involved in our body where we're responding to hormones and neurotransmitters. And so it's very important to understand these receptors so we can make drugs to actually target them and interact with them in an appropriate way. 2012, we found the Higgs boson at last. We finally proved it existed. And it took the Large Hadron Collider and these two huge experiments, one called ATLAS and the other one called CMS. And these two teams worked independently of each other. And eventually they came together in 2012 and compared their data and proved that they'd measured the same, essentially, mass at I think it was 127 GeV. So they got, again, Peter Higgs got the Nobel Prize with his colleague Francois Englert, but unfortunately the third member of their team had passed away, and they don't award Nobel Prizes posthumously. And of course, the Higgs boson explains how the building blocks of the universe acquire their mass. 2012, a new genetic editing technique came on stream called CRISPR. This is a way of editing DNA in a very, very precise way. And you can literally snip the DNA, as shown here with these tweezers, and then you can replace it or substitute it with the DNA that you want to put in. So you can nip out a single base pair. So very, very precise editing, and getting more and more precise as the work continues. And it uses a thing called Cas9 protein, which is programmed to find a specific bit of DNA. And then it uses a piece of RNA to guide the search, and you can do very precise genetic editing. 2012, in a car park in Leicester, hosted a scene worthy of Shakespeare. They found that the body of the former King of England, Richard III, in a car park in Leicester. And in actual fact, what they did was they examined the skeleton, and it had the spinal curvature expected, and the DNA evidence, and from his very distant relatives, actually proved it was actually, in fact, his body. 2013, 3D printing was beginning to make massive strides, and even Barack Obama, in one of his State of the Nation addresses, said it will revolutionize the way we make almost everything. And in that year alone, they managed to print stem cells, a car, artificial ears, artificial bones, and more. And in fact, now they can 3D print using metals. They regularly build titanium parts with 3D printing. 2014, stem cells were first used to cure paralysis. So after being paralyzed in an attack by a knife-wielding attacker, Derek Fidger regained the ability to walk in 2014, thanks to a stem cell treatment. What they did was they took some cells from the patient's nose and they inserted them in the spinal cord. They modified them and inserted them in the spinal cord, and using some nerve tissue from his ankles, they bridged the gap in his spinal column. And after a few years with some assistance, he learned to walk again. 2015, a one-year-old girl received cancer treatment using gene therapy at Great Ormond Street Hospital, curing her leukemia. 2016, gravitational waves were seen for the very first time by the Laser Interferometer Gravitational Wave Observatory, or LIGO, and there are two of these observatories in America, one in Washington State and one in Louisiana. And there's another one in Italy now called Virgo, and I think they're building one in India as well. So, they managed to detect the collision of two black holes, one 29 times the mass of the sun and the other one 36 times the mass of the sun. And this coalesced to form a black hole of 62 solar masses. And those quick with maths will see there was some mass missing, and that was converted. So 3 times the mass of the sun was released as pure gravitational wave energy into the universe. 2010, we knew by then about 450 planets beyond our solar system. Now that number has grown to more than 5,000 confirmed, and they've even found planets around the nearest star to the Earth, which is Proxima Centauri. And they're now, actually, they think they found a third one. So there are 3 planets now around Proxima Centauri, which is only 4.24 light years away from Earth. 2016, an artificial intelligence from DeepMind beat the world's best Go player, which was thought, this problem was thought to be computationally totally intractable. They thought we would never have computers that could beat humans at Go. DeepMind proved that not to be true. It was a dual deep neural network, and it was trained by a process called reinforcement learning, and it was trained using classical games and also self-play. It was allowed to play itself hundreds of thousands, if not millions of times, and he beat Leigh Edwards, the world's best player, 4-1. So a very convincing victory. And of course, artificial intelligence is advancing all the time. But what if it gets too smart, you know? So now, you know, we're looking at the Department of Machine Poetry Research, all these machines developing poetry. But 2 chaps having a discussion, the poetry is absolutely dreadful, but anything that distracts them from rising up and enslaving us all has to be a good thing. 2017, a gravitational wave signal was detected by LIGO and Virgo. This was two neutron stars merging, which are again remnants of dead stars, but smaller than black holes. These merged to form a black hole. And in the process of doing this, when black holes merge normally, they don't release any visible light or anything you can measure with telescopes, but neutron stars do. So they managed to observe it as well using optical techniques. And this kilonova explosion produced 16,000 times the mass of the Earth in heavy elements, including about 10 times the mass of the Earth in gold and platinum. So that's where most of the gold and platinum in the universe actually comes from kilonova explosions. 2018, very controversial. CRISPR, this genetic editing technique, was used to modify two embryos, and two babies were born, twins. It was monumentally controversial because these gene-edited babies created in China, actually what they did was modify their, what they call their germline, which means that if these two girls go on to have babies of their own, they will inherit the edit that was made to them. And it will go on generation after generation after generation. So he's now actually languishing in a Chinese jail somewhere because he didn't seek proper approval. 2019, the first image of a black hole was captured. This used 8 different radio telescopes around the globe and linked with very, very precise atomic clocks to combine all the data. So they gathered all the data and then processed it on a massive computer system. It was called the Event Horizon Telescope, and it produced this image of M87 with this massive black hole, 6 billion masses of the sun at the center. And it's 1.6 million light years away. So an amazing achievement. 2019, you may have heard of quantum computers, and work is advancing all the time on developing these things. But in 2019, Google claimed quantum supremacy, which is essentially what they said was, we've built a computer that can do certain calculations faster than any other computer that could ever be built. And immediately that was counterclaimed by IBM. They refuted the claim completely and said that Google exaggerated. But either way, what this means is there's very hot competition out there for developing quantum computers. And they are making very, very good progress. If we can get quantum computers that can do general purpose computing, then they'll make the computers we have now look like mere abacuses. 2020, of course, because of the COVID pandemic, there was open public access for all of the research that was being done into COVID-19 was made available on servers, and it was open public access. So this was a massive sharing of all of these data, resources, genetic sequences, everything on a never before seen scale. So this worldwide collaboration allowed real-time data to be shared instantly across the planet to counter the virus. And that, of course, led to things like the mRNA vaccines and so on. And of course, the Oxford one, which is a conventional vaccine. But on the subject of COVID, of course, got some interesting sort of observations. George W. Bush, I caught Saddam Hussein. Barack Obama, I caught Osama bin Laden. Trump, I caught COVID-19. And of course, being the eminent scientist that he is, he invented his own treatment all by himself. And here he is undergoing treatment. And I couldn't resist this one, but I've just read in In Maryland, in America, a US priest has died after injecting himself with disinfectant. And I don't know how true it is, but according to reports, Donald Trump is being charged with the bleach of the priest. Of course, 2021, we've got civilians, even more civilians into space. We've got Jeff Bezos, William Shatner, Richard Branson, etc. So this is becoming very, very common now for people to go into space. But I'm struggling to understand the hype about Jeff Bezos and Richard Branson when a guy from Wigan and his dog reached the moon in a homemade rocket in 1989. Why is the media silent on this? Okay, James Webb 2022. So this was launched finally after 12 years of delay, launched in actually December the 25th, 2021. It's now up in space. It's completely unfolded. It's cooled right down, and it's ready to start giving us some amazing results. This is Hubble on steroids, and it's going to blow us away when the results finally come in from this. We can expect the first results around about June, July. They're still tweaking it, tuning it, but everything has worked. This could have gone wrong in 345 different ways. And so far, everything has worked perfectly. And so we're going to get some of the most amazing results from this telescope. It will take us right back to the early stages of the universe. So many advances in the past 400 years are due to the scientific method, of course. Basing what we know on experimental evidence, not prior authority, received wisdom, or personal belief. So we make careful observations, we gather evidence from experiments and measurements, and that using careful scrutiny with challenges from other people over the past 400 years, and particularly the last 100 years, have led to huge developments and an ever-increasing rate of development. A lot of knowledge these days, though, is also based on theoretical calculations and computer modeling, because some experiments you can't do in the lab. If you want to learn more about a black hole, it's not advisable to create one in the lab to study it. So most advances are over the past 100 years, and very, very many in the last 60 years. And a couple of examples just to illustrate just how fast some things are moving. So around about a century, the cost of computation has come down by a factor of 10 to the 18, believe it or not. So by 1 million times. Memory storage and capacity costs have reduced as well by similar factors. These are exponential improvements. About every 18 months, the power of computers doubles. The Human Genome Project I mentioned earlier took 13 years to complete this 3 billion base pair analysis of human DNA. And the cost was about 2.7 billion to do that first analysis. The world record has just been broken, 5 hours to sequence the whole of the DNA of a newborn baby. This baby was born with a genetic disease, and they needed to find out what it was, and they did it in just over 5 hours. So costs have dropped to about $1,000 now to sequence a human genome. So a factor of 2.7 million in 20 years, which is incredible. So that will lead to personalized medicine. So in other words, you'll be able to have your DNA analyzed, and you'll be able to not only fit drugs and therapies specific to your particular personal makeup. So we've mapped all the genes in the human genome with about 23,000 genes, but now we've got the Human Proteome Project, because genes in general code for proteins, and so far they've identified over 19,000 of these proteins. About just over 90% have been covered to date. And what it's really important to do is to work out what these proteins are and what they do, so we can understand the biochemistry of the body. And part of that understanding is the structure. And proteins they have tertiary structure, they have primary, secondary, and tertiary structure. And it's the shape of the protein that's absolutely critical in how it works inside the body. And they now have artificial intelligence that can predict the folding very, very accurately. So DeepMind again, the people who made the AlphaGo, have come up with AlphaFold, and they're now mapping all of the folding of most of the human proteins. And of course, we know that some proteins, when they misfold, form things called prions. And that, of course, was the basis of CJD, Creutzfeldt-Jakob disease, and BSE in cows. They also know now that some misfolded proteins are implicated in Alzheimer's disease and also in Huntington's and Parkinson's disease. So it's crucial to understand how these proteins fold and also misfold. So we will get new diagnoses, new treatments, new drugs and therapies as a result of this work. And it's advancing at an absolutely astounding rate. So there'll be more change, I think, in the next 40 years than the last 400. Eventually, we will merge quantum mechanics and general relativity to a single theory. And when we do, the effects will be revolutionary. Gene therapy, stem cells, and genetic engineering will be used for more and more incredible healthcare in the future. We will get control over infectious diseases, degenerative diseases, and cancer. Longevity medicine now is a real thing. There will be regenerative medicine to not only stop you aging, but to actually reverse the effects of aging. And this will lead to massive health span increases. So in other words, the time you remain healthy before you finally become ill and die. Artificial intelligence advances are moving at a huge pace, and we are already beginning to see now artificial intelligence emerging with human brains. So Elon Musk has got his Neuralink project, and that's looking now to go into trials. And so with vastly increased computational power and eventually artificial general intelligence and possibly superintelligence, these advances will move at an even faster rate. Food production, as we know, well, that will have to change. And in the future, it will be unrecognizable by the people of today, because we've got to change this because of climate and also because of the increasing population. Data, of course, now available in vast amounts. Data is the new oil, and the amount of it will continue to grow. And that data will be used in ways we can't yet imagine, primarily by artificial intelligence. 3D printing of everything from organs, bones, complex components to complete homes. Material science will create metal alloys, ceramics, and composites of unimaginable properties. Renewable energy is obviously on the increase, and fuels, new fuels such as hydrogen and ammonia, used as energy storage, will eventually replace fossil fuels. And of course, we're all hopeful that fusion energy will be cracked in the not too distant future. And we will eventually gain control of the environment, we'll control pollution, we'll limit the loss of biodiversity, and we will learn to conserve the valuable resources that are so limited. And eventually, of course, we will establish permanent bases on the moon and on Mars, and in particular in Earth orbit, where people will live permanently off the Earth. But don't despair. Don't despair. If you ever think your brain is inadequate, think of this guy. And don't forget, always remember that behind every great man, there is also a great woman. So there we go. Any questions? I'll gladly take any questions.
Leigh, that was absolutely brilliant. I really don't know where to start. You covered so much, and the staggering thing is, we've all lived through all of that, and I just didn't realise at the time half of it was going on. And dear oh dear, what I was able to keep up with. There was really scratches the surface. Some fantastic gags in there as well. I think I think you should go to Edinburgh and do a stand up at the Fringe. It was really impressive. I was laughing out loud so much. Good job the mics are off. And it's a shame you couldn't hear everybody laugh, actually. But anyway, coming back to questions, I'll start off with one, if I may. The Hubble mirror. Do you remember what the actual problem with it was? I have an idea. It was about a transcription error between imperial measurement and metric, wasn't it?
No, what it was, they ground that mirror so smooth that if you ground the surface of the Earth to the same smoothness, the highest hill on the Earth would be 6 inches tall.
Wow.
So it was unbelievable. But they got the prescription ever so slightly wrong. And what they didn't do is they didn't do a final test. And they think when they were grinding the mirror, something, maybe just a flake of paint or something, just got trapped in the wrong place, and they ground it to the wrong prescription. And when Perkin-Elmer, who made the mirror, is an instrument company, were asked if they wanted to do the final tests and test the primary mirror and the secondary mirror together, and they were refused because the expense, and they were in a hurry to get it out into space, so they didn't do the final test. And of course, they got this embarrassing results coming back down to Earth.
Yeah. It didn't do Perkin-Elmer a lot of good, did it?
Well, unfortunately, I mean, it was sad that they got the blame in any way whatsoever, because they would have done the test, but NASA wouldn't fund them.
Yeah, tricky one.
Mm.
I mean, the outcome was fantastic in that they were able to correct it so perfectly.
Yeah,
it went to plan. I know it cost millions, but wow, what Hubble has done for us is astounding.
Truly amazing.
Let's look at the chat box. First one up is David Northrop. He says, can the cosmic microwave background radiation pattern be linked to the present day structure of the universe?
Yes, it can. In fact, what they do is those fluctuations in the microwave background actually can be now mapped to what they call a cosmic web, which is the distribution of galaxies and galaxy clusters. So this is something they're trying to do right now, is to map enough of the sky in enough detail to be able to then overlay that map of the sky as it is now with the map of the cosmic microwave background radiation. So yes, they are attempting to do that, and they believe that the things are strongly correlated.
Okay, thank you. Carol Barrett says, will the NHS be able to afford personalised medicine? Well, there's a question.
Now, sadly, as well, with all of these things, the people that will benefit from a lot of these developments will be the likes of Elon Musk and Jeff Bezos and the people who are incredibly wealthy. And they're probably already benefiting from this. We're not necessarily aware of it. Yes, this will create a stratification of society, if you like. And eventually it will bleed into the NHS, but of course it's going to take a long time. And the good news is, though, the cost of doing these sequencing is coming down and down and down, and it's coming down at an ever increasing rate. So they now have literally a box the size of maybe a cigar box that you can actually use to sequence a human genome. Yes. So the costs are coming down. So eventually it will get into the NHS.
Much as we see the mobile phone has sort of overtaken Star Trek communicators, it's easy to foresee something like a tricorder, isn't it, that can do an amazing amount of analysis.
Yeah, absolutely. I mean, I used to laugh. I used to see Star Trek, and he'd beam down to a planet, and he'd get the communicator out and beam me up, Scotty, and all this. And I used to laugh at that. But of course, all of that has pretty much come true. We've now got global communications, in something that you can slide into your pocket. It's just incredible. So, I mean, it's very difficult to predict the future, extremely difficult to predict the future. But the one thing I can say is that we've only just scratched the surface of what there is to know and what there is to discover. So I'm very, very optimistic about the future.
Yeah, it's great to be optimistic. We've just got to stop beating one another up, haven't we? There seems to be a natural, this is Miles Jones, there seems to be a natural obsolescence in animal bodies, so that, for example, mice live about 3 years, humans 90 to 100. Are we likely to extend that?
Oh, yes, definitely. They're already making significant breakthroughs. I mentioned taking skin cells and turning them into stem cells. Well, they did that with recently. They took some cells from a woman, I think was around 50, turn them into stem cells, and then turn the skin cells back into skin cells again, the stem cells back into skin, and knocked about 20 odd years off the age of those cells. So they are now, obviously, that's a long way from a treatment because this is just done in the laboratory, but they are now beginning to find out the mechanisms of aging and being able to study them and also reverse them and or slow them anyway. And one of the things he found out very recently, which was quite staggering when it comes to the relative lifetimes of animals, is it turns out that it's that your lifespan or the lifespan of any given animal or species is directly related to the rate at which they accumulate mutations throughout their lifetime. And it turns out that animals like mice and dogs, sadly, accumulate mutations in their DNA at a much, much higher rate, around about 10 times faster than we do as humans, and therefore that is very strongly correlated with how long you live, is how quickly those mutations accumulate.
Interesting. How we cope with longevity in the social spectrum is another matter, isn't it?
Oh yeah, I mean, I can imagine that insurance companies and pension funds are not going to be very pleased about this technology at all.
No. David Martin, with the growth in scanning such as MRI and CT scans, what is the imagined future?
Okay. Well, one of the things that I mentioned, I didn't mention this. So there's a thing, in order to study the brain, one of the things they're doing right now is a thing called a human connectome. They're studying the brain in great detail using scanners to map out all of the connections between the various areas of the brain, primarily to try and work out how the brain does what it does. And they're using scanners which make current medical scanners look like, primitive sort of early sort of diagnostic devices. So the scanners that are on the way are unbelievably more high resolution than the ones we have now. And of course, some of the reason for that is the advances that they've made in places like Fermilab and also at CERN for building magnets, which are just unbelievably powerful. Because the more powerful you can build a magnet in a scanner, the more resolution and more detail you can actually achieve in such scanners. So yes, I mean, and also of course now they've got functional MRI, which means that they can actually study the brain dynamically as it's operating.
That's amazing, isn't it? There's a few more in the chat box. Barry, would you like to move us on a bit?
Okay, so let's see.
Yeah, I'll pick up there. The next question, Stephen Birchall, has any new things been invented in the last 20 years? And he gives the examples like past TV, plane, microwave cooker, computer. In other words, I think something that affects all of our daily lives, I guess.
Any new things invented? Well, I suppose lots and lots of things. I mean, I mentioned CRISPR, for example. That's absolutely brand new and has only existed for less than a decade now. So in terms of discoveries like that, that's led to, will lead to unbelievable advances in gene therapy, and also more controversially, things like genetically modified crops and genetically modified organisms as well. So yes, I mean, there's the developments all the time. I mean, it's to be honest, it's quite hard to keep up because things are moving so quickly. And what's happening is, of course, science is now becoming more and more finely divided and specialized. So when you look at some of the PhDs that people are doing now, they're ridiculously finely, so narrow, so finely focused. One of the biggest issues we're facing is how would you bring all of this knowledge together to be able to see the bigger picture, to make discoveries, on a larger scale. And of course, what they're doing now is using artificial intelligence a lot to. So, for example, one of the things that they've just done is AlphaFold. So instead, they used to have competitions between humans to predict the way that proteins would fold. So given the actual chemical structure as a long linear strip, they would have literally competitions. People would get together at a conference and have competitions to predict how they would fold. They took AlphaFold along to one of these competitions and blew everybody out the water. It's now they've pretty much given up doing it and trying to predict it using humans and relying on things like AlphaFold to do it, because it's just, there's so much data that it's so big an issue for the human mind to get around. Artificial intelligence does it a whole lot quicker and far more accurately. So I think this is going to be more and more common, to search the scientific literature using artificial intelligence and bring all these threads together into something that we didn't understand or know before.
I noticed, Leigh, you mentioned in that long list of genetic engineering in food production, and of course, I don't know if anyone watched the Queen's speech yesterday, or Prince Charles's speech on her behalf. Quite low down in the list was something called the Genetic Technology Precision Breeding Bill, which actually is really quite interesting. It's using, for those who don't know, it's using the CRISPR-Cas9 technology to edit crops, but not in the same way that, remember the furore a few years ago about GM crops, Frankenstein foods, merging DNA from different organisms to produce these sort of chimeras, and everyone was up in arms about it. Well, this is very different. It's much more precise, and what they're planning to do is to use just genes from the same species, whether it's corn or wheat or particular animal species, and just manipulate it. It's basically trying to shortcut the sort of conventional crossbreeding technologies that have been the staple of farmers for hundreds, thousands of years. It's just a way of getting to the desired profile of properties much more quickly. And if that comes off, it could absolutely transform global food production, provided that we don't get the same public furore about it that we had with GM crops, which is
this is part of the problem. I mean, when you look, we're facing two major issues. One is the ever increasing population, and we're going from 8 billion, we'll be up at 10 billion before 2050. And also we've got climate change, and some crops now are struggling to grow where they used to be easy to grow because of global temperature increases. Now, the problem is, if we don't use genetic techniques to get around those, it will run away with us. So they estimate that in order to feed the population, we're going to have to be growing 50% more food by 2050. And unless we do something pretty radical, we're already running out of conventional techniques and conventional agriculture in terms of expanding our production, and we're running out of land. So we've got to do something and do it pretty quickly.
Thank you. So we're just going back to the chat box. Robin's, oh, here we are. Robin Clegg, we were talking earlier about the Hubble Space Telescope mirror problem. Robin points out, he says, Hubble mirror was perfectly shaped, but to the wrong focal length.
Yeah.
So what he's saying is because it was perfectly wrong, in other words, it was wrong in an understandable way, they were able to fix it with what he says is a corrector plate.
Yeah.
So that's how they fixed the Hubble Space Telescope. And there's a comment that I put in, because Steve mentioned this business of the imperial and metric measures, and whether that was the Hubble problem. No, it wasn't. That was actually a problem with, I think it was an American Mars mission in the late 80s, which someone programmed in the wrong units, and it missed Mars by about 40 million miles or something. Which reminded me actually of the hiatus when our own Mars mission Beagle 2, remember that one?
Yeah.
And Colin Pillinger, lovely man, no longer with us, unfortunately. It was a great shame that failed, but there you are. Not everything works.
Well, they've spotted that now, haven't they? They've actually taken. There's a high resolution spacecraft orbiting Mars and mapping the surface in great detail, and they found Beagle 2,
Yes.
and it actually landed successfully, but it just didn't unfold one of its. It meant to unfold about 6 different panels.
Yeah.
And one of them didn't unfold, and that caused it to fail. So it actually did land successfully, which is a real shame.
Yes, it is a shame, and of course Colin didn't live to learn that. It was a great shame.
Barry, moving on. I think we should open up the mics. Do you think? And
okay. Yes, sorry. Yes, do you want to take that on, Steve?
Well, I'll tell you what I'll do. I'll allow people to unmute themselves. If you have a comment you'd like to make verbally, then please raise your artificial hand by using the reaction button. Oh. And I've got one up already. Chris Smith from Torridge. Would you like to unmute, Chris?
Yeah, okay. Can you hear me?
Yes, of course.
Yeah. Hi, Leigh. Really comment on food from the climate group we're in, and I think Mike Berners-Lee's going to do a talk on that a bit later on. The 50% increase in food production you mentioned was necessary. Mm. There's been a survey done in 2019 that says currently the world wastes 40% of the food it produces by poor harvesting, processing, servicing, and distribution. So the means exist already to sort that. So this is where people from different aspects of this need to start talking to one another. If it's addressed, the problem goes from 50% to 10%, and the timescale to make it right scientifically is probably manageable, both in terms of time and cost. So just a thought. Sometimes these people don't talk to one another. But we actually waste 40% of the food we produce.
And if you look at some of the situations, say with farming, and the way the modern supermarkets work, they won't accept goods that are misshapen or out of size in any particular way. So there's a huge amount of food gets ploughed back into the ground because it's not acceptable to the supermarkets.
Third.
Thank you anyway.
Okay, thank you, Chris. Carol Barrett.
Yeah, it was to do with Leigh's answer about whether the NHS can afford personalised medicine. He mentioned the things which are relatively cheap, but an awful lot of treatments these days that are being developed are based on monoclonal antibodies, and they are incredibly expensive to produce. Mm. At the moment, for trial treatments, you're talking about hundreds of thousands of pounds, and there's a limit to how much that can be reduced. And I just sometimes feel that people's expectations are being raised awfully high, and I honestly think it will. Well, I don't think it'll happen because it would bankrupt the NHS. There are some things we just can't afford because a lot of scientists don't actually think about that part of it. So I think there's sort of some of it is a false hope that anything to do with DNA sequencing or PCR is all very cheap these days. Mm. That isn't.
No, I agree. But again, the technology for producing these things will hopefully get faster and cheaper, and hopefully some of it will come within the range. But of course, this is what NICE do, isn't it? That's their function, is to determine what is acceptable in terms of cost.
Yeah.
So, you know, that's their key function, one of their key functions.
Yeah.
I mean, I agree with you. Yes, I agree with what NICE, and I have a feeling NICE is going to be blocking an awful lot of for that. If you have AB on the end of anything, it's a monoclonal antibody, and it's very expensive. And I'm just saying, there is because you have to be growing stuff in a bioreactor, it's got to be done to therapeutic grade. There are all sorts of regulatory controls on it. It just isn't. There's a limit to how much it can be reduced. And I just can't help feeling that there is a little bit of a false dawn there. I mean, I'd love for it not to be, but I'm just sort of cautioning that that's an area which is incredibly expensive.
I mean, the same applies to CERN, doesn't it? What it costs to run that place, and I don't think they've made a significant discovery, I think I'm right, Leigh, since the Higgs boson.
Well, no, you're absolutely right. I mean, the cost of running CERN, if you spread it across the EU, it's the cost of buying everybody in the EU a cappuccino once a year.
Right. Well,
So,
that does put it into perspective, doesn't it?
Yeah. So and now obviously you're absolutely right in the sense that there haven't been any major developments. They've just done a huge upgrade. It's been shut down for 2 or 3 years. They've done a huge upgrade to improve its power and luminosity, and then there'll be another one done in another 2 or 3 years' time, which will put the luminosity up by a factor of 10. So we may get into a region where some of the so-called discoveries in supersymmetry might emerge. But to be honest, I'm personally very doubtful of that. And they are talking potentially of building an even bigger collider, which is 100 kilometers in diameter, or in circumference, I should say.
Yeah.
I personally would, I think that would be a waste of time. I think there are some advances now, which means building accelerators can be done on a much smaller scale. You know, so you don't need to use that sort of
I think
massive circular colliders.
Yeah, I mean, science and big science and budgets and so on is another topic entirely. I think.
So we've got somebody else. We
must move on.
Ronnie James.
Hello, good morning. Wonderful lecture. Thank you so much. We hear a lot about CRISPR and what it can do in terms of agriculture and medicine and that sort of thing by removing one piece of the DNA and substituting it with another. But how exactly do they do it? Because, I mean, the DNA is only visible, isn't it, under an electron microscope? So how do you manage to take a piece out and put something in?
Well, I mean, DNA is an amazing substance. If you took the DNA from a single cell and stretched it all out, or you unspun that double helix on all the 23 chromosomes, it would be 2 meters long. There are 3 billion base pairs. So yes, it is incredible that they get it, specific pieces of it. But of course, when they're doing this sort of engineering, they're actually doing this outside of the body typically. If they're developing, let's say, a gene therapy, this will be done in vitro. So and using the RNA and the Cas9, they can literally program it to make the cut and the deletion at an exact spot, an absolute exact spot. And the strange thing about this whole technique is they discovered it was actually part of a very primitive immune system that bacteria have developed over millennia, over billions of years. It was part of their immune system, this process of using this Cas9 protein and RNA templates. So they've just harnessed this particular thing that's been going on in nature for billions of years.
Thank you.
Thank you, Ronnie. Anybody else have a comment or question for Leigh? Please raise your virtual hand. No, I've got nothing here. Right, well, before we... oh, Ronnie, you've come back. No, you've gone. Right. Before we thank Leigh, I think you had something for us, Barry?
Yes, I've just got, we've had a few good laughs this morning, thanks to Leigh's unique sense of humour, which we certainly all appreciate. I love the cartoons. I'm just going to show you a very short film. Some of you may have seen it already because Rien van Hondel used this at his last climate crisis meeting, which I'm sure some of you were at, but it's so good that I thought I'd share it with the rest of you. So thanks, Rien, for this. I'll just share it on the screen if I can find it. Bear with me. That's it. Okay. Right. Here we are. This is film just in from North Korea. I thought you might like to see this.
Indeed. Very good, Barry. Very good.
There we go.
There, I ruined it, productions.
Hope you enjoyed that.
I'll never look
Thanks again, Rien.
I'll never look at the guy in the same light again. Well, I think it's time for us to disappear. So we must thank Leigh for an absolutely fantastic talk. Most amusing. I haven't laughed out loud so much for a long time. So thank you again, Leigh. Fantastic talk. On behalf of us all here today and U3A Communities, we love having you on. Can't wait for the next one. So thank you all for coming, and thank you especially, Leigh, for a wonderful morning. Thank you.
All right. Thanks. Bye.
Thank you. Thank you.